In this video, I'm going to take a look at trigonometry beyond the three ratios that you explore in core mathematics. If I give you a particular angle and it's in a right-angled triangle, then I'm allowed to use trigonometric ratios. You'll remember that in the Cartesian plane, the three ratios that I could have had could have been sine of my angle, cos, cosine of my angle, or tan, tangent of my angle. And you'll remember that these ratios can be represented as a numerical ratio, which is a side over a particular side from the triangle. If I had the sine ratio, then I would have used y all over r. The cosine ratio uses x all over r, and the tan ratio uses y all over x. The x measurement is the horizontal measurement. The y measurement is the vertical measurement, and the radius is the hypotenuse. It stands to reason, though, that if I have got ratios, and the ratios could have been y over r, then there should also be a ratio of r all over y. Now that ratio also has a name. It's the reciprocal of sine alpha, and I call that reciprocal cosec of alpha. Similarly, the reciprocals for cos alpha being r all over x, I call sec of alpha. And lastly, the reciprocal of tan of alpha is cot of alpha. And that would be tan's reciprocal, in other words, x all over y. You now can see that we have 6 very nice ratios that we can use in our right-angled triangle. If I had wanted to, I could obviously have written cosec alpha as 1 all over sine of alpha. Sec alpha could have been written as 1 all over cos of alpha, and cot alpha could have been written as 1 all over tan of alpha. Using these 6 ratios, I'm going to explore some identities. These identities all use square numbers, and so I call them square identities. The first identity you'll recognize from your core maths. It starts by saying, what would the answer have been if I had sine squared of alpha and I added that to cos squared alpha? Well, sine of alpha uses the numerical ratio of y all over r. If I square that and add that to cos's ratio, which is x all over r squared, do power times power. In other words, I'm going to get y squared all over r squared plus x squared all over r squared. And I write that so that it is all over a common denominator of r squared. I'm going to have y squared plus x squared all over r squared. And you should know that y squared represents the vertical. X squared represents the horizontal distance squared. And if I take the vertical distance squared added to the horizontal distance squared, that is the same as the radius squared. And this you'll remember from Pythagoras. In other words, I've now got r squared all over r squared, which is 1. So my first square identity is going to be that sine squared of an angle plus cos squared of the same angle is equal to 1. My second square identity starts with the expression of 1 plus tan squared of my angle. Now, changing this ratio to its numerical ratio, that could give me the statement of 1 plus tan squared of alpha is the same as writing y all over x all squared, which is going to be y squared all over x squared. Now, finding a common denominator, we can see that my common denominator must be x squared, and so I have x squared plus y squared all over x squared. We know by now, though, that if I write x squared plus y squared, I've got the sum of the squares of the two shorter sides of my right-angled triangle, and that could have been written as r squared all over x squared, which is the same as r all over x squared. Now, can you see that r all over x is the reciprocal of cos of the angle? And so, in other words, that is the same as sec squared, the reciprocal of cos of my angle. In other words, I've now discovered my second identity, which states that if I've got 1 and I add tan squared of the angle, that can be written as sec squared of the same angle. My last square identity starts with the statement 1 plus cot squared of my angle. What is the numerical ratio for cot of alpha? That is if I write it as of x squared all over y squared. Remember that cot alpha is the reciprocal of tan of alpha. Now, finding my LCD again, my LCD is going to be y squared, which gives me y squared plus x squared in my numerator. X squared plus y squared is the same as r squared, still all over y squared, which is the same as r all over y all squared. Have you noticed that this is the reciprocal of sine of alpha? In other words, that is going to be cosec squared of alpha. So finally, our last square identity is going to be if I have 1 plus cot squared of an angle, and that could in fact have been written as cosec squared of the same angle. In other words, there are 3 square identities that you have to learn very well. Sine squared alpha plus cos squared alpha could have been written as the number 1. 1 plus tan squared alpha could have been written as sec squared alpha, and 1 plus cos squared alpha could have been written as cosec squared alpha. As each of these has a side which has got 2 terms, instead of writing sine squared alpha plus cos squared alpha is equal to 1, I could have written sine squared alpha is 1 minus cos squared alpha, or cos squared alpha is 1 minus sine squared alpha. And similarly, I could have moved terms around with the other 2 square identities. So you need to learn all forms that you could recognize these identities.